Hello there, and welcome to Z Science. I'm so glad you're here. Maybe it's been a long day, or maybe you like to fall asleep thinking about distant planets and drifting moons instead of counting sheep. Either way, tonight's journey is for you. Just rest now. Let your breath slow, your thoughts soften, and your body grow light, as if gravity has loosened its grip and you're quietly floating through space. Tonight we'll drift through the solar system in soft spirals, from glowing planets and dusty rings to shadowed craters and frozen oceans beneath the ice. A story told not in numbers but in magnetic storms, tilted axes and moons that glow in the dark. From sideways worlds and diamond rains to ancient sunlight crossing the void, every orbit hides something strange and beautiful. If this calm space journey helps you relax, please tap like and subscribe so more sleepy souls can find their way here. Neptune's winds break the speed of sound. Despite being the farthest known planet from the Sun, Neptune hosts the fastest winds in the solar system. These winds whip through its upper atmosphere at speeds exceeding 2,000 kilometers per hour, faster than the speed of sound on Earth. That is roughly 5 times the speed of a commercial jet. The winds likely derive their energy from the planet's internal heat, which continues to radiate outward despite the freezing conditions at its surface. Neptune's atmosphere is composed mostly of hydrogen, helium, and methane, and the winds carve massive storm systems into the planet's pale blue clouds. It is a frozen world in constant supersonic motion. Mars holds a canyon the size of a continent, stretching more than 4,000 kilometers across the Martian equator. Valles Marineris is the largest canyon system in the solar system. It would span the entire width of the continental United States. In places, it plunges over 7 kilometers deep, more than 5 times deeper than the Grand Canyon. Scientists believe it formed through a combination of tectonic stretching, volcanic activity, and erosion. Unlike Earth's canyons, which are typically carved by rivers, these chasms may have opened as the planet's crust cracked and pulled apart. It is a scar in Mars's surface, hinting at a violent geological past now frozen in time. Venus has no magnetic field. Despite being similar in size, mass, and composition to Earth, Venus lacks one crucial planetary feature: a global magnetic field. Earth's magnetic shield is generated by the motion of molten iron in its outer core, protecting the planet from solar radiation. Venus, however, seems to have a sluggish or possibly solid core, which may prevent the kind of dynamo effect needed to create a field. Without this protection, Venus's atmosphere is constantly bombarded by solar wind, which has stripped away lighter elements over time. The absence of a magnetic field helps explain why Venus, once possibly Earth-like, became a furnace world. Diamonds may rain on Uranus and Neptune. Deep within the atmospheres of Uranus and Neptune, conditions may be extreme enough to create something extraordinary. Falling diamonds. These icy giants have thick layers of methane gas, and under immense pressure and heat, scientists believe the methane can break apart, releasing carbon atoms. These carbon atoms then compress into crystalline structures, forming tiny diamonds that rain down toward the core. Laboratory experiments have simulated this process, showing how hydrocarbons can condense into diamond under the right conditions. If this theory is correct, then storms of glittering crystals might drift through the deep blue. Darkness of distant gas giants. Earth is the only planet with plate tectonics. One of Earth's most distinctive and life-enabling features is its system of plate tectonics, a dynamic network of shifting crustal plates that float atop the mantle. These moving plates create earthquakes, build mountains, and recycle carbon dioxide, regulating the climate over geologic time. So far, no other planet shows clear evidence of this process. Mars and Venus have surface fractures and volcanic features, but they appear geologically stagnant by comparison. Earth's plate tectonics may be part of what makes it habitable, driving the long-term cycles that stabilize temperature, support oceans, and enable the movement of continents over eons. Some asteroids have their own moons. While we often picture asteroids as solitary wanderers, some of them actually have moons, smaller bodies orbiting around them. These tiny satellites are usually captured fragments or co-formed companions. The first discovered asteroid moon was Dactyl, which orbits the asteroid Ida, revealed by the Galileo spacecraft in 1993. Since then, dozens more asteroid moon systems have been found, including some with multiple moons or strange binary arrangements where two asteroids orbit each other. These miniature systems show that even in the vastness of space, gravity can link the smallest of objects into quiet, drifting partnerships. Mercury has a ghostly exosphere instead of a true atmosphere. Unlike Earth, Mercury does not have a thick atmosphere to retain heat or scatter light. Instead, it has a thin, tenuous shell of particles known as an exosphere, a near vacuum where atoms bounce around without colliding. This exosphere is made of atoms blasted from the surface by solar wind and micrometeoroid impacts, including sodium, potassium, and oxygen. Because Mercury lacks the gravity to hold a real atmosphere, these particles constantly escape into space and are replenished from the surface. The result is a ghostly, shimmering envelope of scattered atoms, invisible to the eye but detectable with the right instruments. The Sun loses millions of tons of mass every second. Every second, the Sun converts over 4 million tons of its own mass into energy through nuclear fusion. In its core, hydrogen atoms are fused into helium, releasing light and heat that power our solar system. This energy radiates outward in all directions, warming planets, driving winds, and fueling life on Earth. Though the loss is minuscule compared to the Sun's total mass, over billions of years it adds up. Eventually, the Sun will exhaust its hydrogen fuel and begin to change. But for now, it continues to burn steadily, sacrificing a tiny part of itself with every passing second. Saturn's rings are slowly disappearing. The beautiful rings that encircle Saturn are not permanent. They are gradually falling into the planet, drawn in by gravity and pulled down by Saturn's magnetic field. This process, known as ring rain, involves streams of ice particles and charged material drifting inward over time. Observations from the Cassini spacecraft suggest that the rings may be less than 100 million years old, young by planetary standards, and could vanish entirely in another few 100 million years. Though they seem timeless, Saturn's rings are a temporary feature, a shimmering spectacle that will one day fade into memory. Mars experiences planet-wide dust storms. Mars is known for its rusty, desert-like landscape and for the colossal dust storms that sometimes engulf the entire planet. These storms can last for weeks or even months, blocking out sunlight and reshaping the surface. The dust is incredibly fine and can stay suspended in the atmosphere, creating a hazy reddish glow. Some storms begin as small gusts, but can grow rapidly due to feedback loops between heat, wind, and topography. In 2018, such a storm led to the end of the Opportunity rover's mission as its solar panels were choked with dust. Even without rain or oceans, Mars remains an active and restless world. Europa may have a salty ocean beneath its ice. Beneath the frozen shell of Jupiter's moon Europa, there is strong evidence for a vast subsurface ocean of liquid water. Tidal forces from Jupiter's gravity flex Europa's interior, generating heat that may keep the ocean from freezing solid. The surface is streaked with dark lines and ridges, signs of shifting ice, and spacecraft have detected magnetic signatures and chemical traces that support the ocean hypothesis. What makes Europa especially fascinating is the possibility that this hidden sea could harbor life. It is a dark, alien ocean, warmed from below, sealed beneath ice, yet potentially rich with ingredients for biology. Mars has a volcano taller than Everest. Olympus Mons, the tallest volcano in the solar system, towers nearly 22 kilometers above the Martian plains, almost 3 times the height of Mount Everest. It is so wide that it would cover the entire state of New Mexico. Formed by repeated eruptions over millions of years, Olympus Mons grew so large partly because Mars lacks plate tectonics. On Earth, volcanic hotspots shift over time, creating chains of islands like Hawaii. But on Mars, the crust remains still, allowing magma to erupt in the same spot again and again. The result is a single massive shield volcano that looms silently in the Martian night. Saturn's rings are paper thin. Saturn's majestic rings stretch more than 280,000 kilometers across, yet they are astonishingly thin. In most places, the rings are less than 100 meters thick. That is thinner than many city buildings. Made mostly of water ice, the ring particles range in size from grains of dust to house-sized boulders. When sunlight passes through the ring zone, they nearly disappear from view like a sheet of glass turned sideways. Their flatness is maintained by the planet's gravity, the self-organization of billions of icy fragments, and the influence of small shepherd moons. From a distance, they appear solid, but up close, they are delicate and ethereal. Earth is the densest planet. Of all the planets in the solar system, Earth is the densest. This means it packs more mass into each cubic centimeter than any other planet, thanks to its composition of metal-rich core and silicate mantle. Earth's density is about 5.5 grams per cubic centimeter, higher than that of Jupiter, despite the gas giant's far greater size. This high density plays a key role in generating Earth's magnetic field, which comes from the motion of molten iron in its outer core. Our planet's internal structure is compact, heavy, and layered, shaping not just its gravity, but its geology and protection from space. The sun vibrates like a musical instrument. Though we cannot hear it with our ears, the sun constantly rings with pressure waves that ripple through its blazing layers. These oscillations, caused by rising and falling currents of plasma, generate ultra-low frequency sounds far below human hearing. Scientists study these vibrations through a technique called helium. By tracking how the waves travel and bounce within the sun's body, researchers can map its internal structure, much like geologists use seismic waves to explore Earth's interior. These solar songs reveal hidden flows, magnetic activity, and the dynamics of fusion deep within the core. In a way, the sun is always humming, quietly revealing its secrets through vibration and rhythm. Venus rotates backward. Unlike most planets in the solar system, Venus spins in the opposite direction, a phenomenon known as retrograde rotation. On Venus, the sun rises in the west and sets in the east. Even stranger, its rotation is incredibly slow. A single day on Venus lasts longer than its year, taking 243 Earth days to complete one rotation. Scientists are not certain why this happened, But one possibility is a massive collision early in its history that altered its spin. Another theory suggests tidal interactions with the Sun slowly flipped its axis over time. Whatever the cause, Venus stands alone as a slow-turning world with a reversed rhythm. Jupiter has more than 90 moons. The gas giant Jupiter is not just the largest planet, it is also the king of moons. As of now, astronomers have identified over 90 natural satellites orbiting it, and new ones are still being discovered. Its 4 largest moons, Io, Europa, Ganymede, and Callisto, are known as the Galilean moons, named after Galileo Galilei, who first observed them in 1610. But beyond these giants lies a swarm of smaller, irregular moons, many captured from passing objects. Some of them orbit backward, some are just a few kilometers across. Together, they form a miniature solar system in orbit around Jupiter. Bound by the planet's immense gravity and history, Mercury hides ice in its shadows, scorching during the day and freezing at night. Mercury is not where you would expect to find ice. Yet, it is there. At its poles, deep inside craters that never receive sunlight, temperatures remain cold enough for water ice to exist. These permanently shadowed regions act like natural freezers, preserving ice for millions of years. Radar reflections from spacecraft like Messenger have confirmed the presence of these bright icy patches. Scientists believe the water may have arrived from comet impacts or ancient volcanic out. In the heart of one of the hottest planets, ice survives, locked in darkness, shielded by crater walls from the relentless solar blaze. Pluto's heart may hide an ocean. The bright heart-shaped feature on Pluto, known as Sputnik Planitia, is not just a scenic landmark. It may be the surface expression of a vast underground ocean, though Pluto is far from the Sun and cold enough to freeze nitrogen. Evidence from the New Horizons spacecraft suggests that a layer of liquid water might lie beneath its icy crust. The weight of the heart-shaped basin and its apparent geological activity hint at a slushy, convecting subsurface. If this ocean exists, it could be kept liquid by heat from radioactive decay and insulating ice layers above. Even in the frozen reaches beyond Neptune, a hidden sea may quietly persist. The asteroid belt is mostly empty space. Despite popular imagination, flying through the asteroid belt would not be like dodging rocks in a science fiction movie. In reality, the belt is vast and sparsely populated. Located between Mars and Jupiter, it contains millions of rocky bodies, but they are separated by enormous distances. A spacecraft passing through would almost never encounter an obstacle. The entire mass of the asteroid belt is less than 5% that of the Moon. Its largest members, like Ceres and Vesta, account for most of that. The rest are scattered fragments from the early solar system. Ancient building blocks that never formed into a planet. Uranus rolls around the Sun. Most planets spin like tops, tilted slightly on their axis. But Uranus is tipped so far over that it essentially rolls along its orbital path with an axial tilt of 98 degrees. This means its poles point almost directly at the Sun during parts of its orbit, giving it extreme and bizarre seasons. Each pole experiences 42 years of daylight, followed by 42 years of darkness. The cause of this tilt is still debated, but it may have been knocked sideways by a massive collision long ago. Uranus's tilted orientation gives it one of the strangest climates in the solar system. Jupiter's radiation belts are deadly. Jupiter is surrounded by a massive magnetic field, the strongest of any planet. And within it are radiation belts so intense they would destroy unprotected spacecraft in hours. These belts are filled with charged particles trapped by the planet's magnetic field. forming zones of high-energy radiation similar to Earth's Van Allen belts, but vastly more powerful. Jupiter's largest moons are exposed to this radiation too, which can affect their surfaces and potential habitability. To survive in orbit around Jupiter, spacecraft must take special shielding measures or stay in the radiation paths. It is a beautiful world, but one wrapped in invisible danger. The Sun contains nearly all the mass in the solar system. At the heart of our solar system, the Sun dominates, not just with light and gravity, but with sheer mass. It holds over 99.8% of all the mass in the solar system. That means everything else, all the planets, moons, asteroids, comets, and dust, makes up less than 1/4%. Its gravitational pull binds everything in orbit, from tiny grains in the asteroid belt to distant comets in the Oort cloud. This immense mass is what fuels the fusion reactions at its core, converting hydrogen into helium and flooding space with the energy of day dot. There are more dwarf planets than classical planets. Beyond Neptune lies a scattered population of icy, distant objects, many of which are large enough to qualify as dwarf planets. Pluto is the most famous, but it is just one among many. Others like Eris, Haumea, and Makemake share this status, and more candidates are constantly being discovered in the Kuiper Belt and beyond. In fact, the number of dwarf planets may vastly exceed that of the 8 classical planets. These small round worlds are relics of the early solar system, untouched and ancient. Though they orbit in the cold shadows, they hold clues to the formation of everything we know. A day on Venus lasts longer than its year. Venus has one of the slowest rotations of any planet. It takes 243 Earth days to spin once on its axis. Meanwhile, it only takes 225 days to complete one orbit around the Sun. That means a single day on Venus, from one sunrise to the next, is actually longer than a full year. This sluggish spin also contributes to extreme surface conditions with temperatures hot enough to melt lead. Combined with its thick, acidic atmosphere and crushing pressure, Venus is a world of slow, simmering heat and eerie sunless days. Titan has lakes made of methane. Saturn's largest moon, Titan, is the only other place in the solar system known to have stable liquids on its surface, but they are not made of water. Instead, Titan's lakes and rivers consist of liquid methane and ethane flowing across a landscape sculpted by cold chemistry. Its thick atmosphere, rich in nitrogen, forms weather systems that include methane rain and even seasonal storms. Some of Titan's lakes are vast, stretching hundreds of kilometers. Beneath the icy surface, scientists believe a subsurface ocean of water may also exist. Titan is a world with familiar shapes, clouds, rivers, and coasts built from alien substances. The moons of Mars may be captured asteroids. Mars has 2 tiny misshapen moons, Phobos and Deimos. They look more like asteroids than traditional moons, irregular, rocky, and pockmarked with craters. Many scientists believe they were once part of the asteroid belt and were captured by Mars's gravity long ago. Their strange orbits and low densities support this idea, though some alternative theories suggest they may have formed from debris after a massive impact. Phobos is slowly spiraling toward Mars and will eventually break apart or crash into the planet. Deimos is drifting away. These little moons are quiet passengers in orbit, remnants of a chaotic past. Jupiter glows with its own heat. Unlike most planets, Jupiter gives off more energy than it receives from the Sun. This internal glow comes from leftover heat from its formation. a kind of gravitational energy released when the planet's immense mass collapsed together. Over time, it continues to contract slightly, generating heat in the process. This warmth drives Jupiter's turbulent weather systems, including its giant storms and swirling bands. In the infrared spectrum, Jupiter shines brightly like a smoldering coal beneath cloud layers. It is not a star, but it almost became one. If it had been just a bit more massive, it could have ignited into a failed sun. Neptune was discovered through math. Unlike other planets, Neptune was not discovered by simply looking through a telescope. Instead, astronomers noticed irregularities in Uranus's orbit, tiny deviations that could not be explained by known gravity. Two mathematicians, working independently in the 1840s, used these strange motions to predict the location of a hidden planet. When astronomers pointed their telescopes toward the calculated position, Neptune was there. It was a triumph of celestial mechanics, confirming that unseen forces could be mapped through mathematics alone. Neptune was the first planet found on paper before it was seen through glass. A world brought to light by numbers. Saturn's North Pole has a hexagon. At Saturn's North Pole, a massive cloud pattern spins in the shape of a nearly perfect hexagon. This six-sided jet stream spans over 30,000 kilometers across, wider than Earth, and has persisted for decades, possibly centuries. Scientists believe the hexagon forms from the way Saturn's atmosphere rotates and interacts with stable waves of air trapped around the pole. In lab experiments, similar shapes appear when rotating fluids at different speeds. The fact that such a geometric shape can emerge naturally in a planetary atmosphere is still one of the more surreal and elegant phenomena in the solar system. The Sun's atmosphere is hotter than its surface. It might seem intuitive that the hottest part of the Sun would be its surface, but it is not. The visible surface, or photosphere, has a temperature of about 5,500 degrees Celsius. Yet, the outer atmosphere, known as the corona, can reach over 1,000,000 degrees. This unexpected increase in temperature has puzzled scientists for decades. One theory suggests that magnetic waves from deep within the Sun transfer energy upward and heat the corona from below. Another possibility involves tiny solar explosions called nebulas. Either way, the Sun's outer layers glow with mysterious searing heat far beyond their source. The Kuiper Belt is full of icy worlds. Beyond Neptune lies a wide ring of icy objects known as the Kuiper Belt. It stretches billions of kilometers from the Sun and is home to countless frozen bodies, including Pluto, Eris, Haumea, and Makemake. These are not stars or planets, but ancient remnants from the solar system's formation. Some are spherical and classified as dwarf planets, while others are irregular, tumbling through space. The Kuiper Belt is similar in structure to the asteroid belt, but it is far colder and contains more primordial ice. It is a fossil zone, a frozen archive of the materials that built the outer worlds. The Oort cloud may stretch a light year from the Sun. Far beyond the Kuiper Belt, even beyond Pluto's furthest reach, lies a hypothetical shell of icy bodies known as the Oort cloud, though never directly observed. This vast sphere of frozen debris is thought to encircle the solar system and extend nearly a light year away. It is the likely source of long-period comets, which appear from the depths of space with unpredictable orbits. These distant objects are only weakly bound to the Sun, and a passing star or galactic tide could send one hurtling inward. If the Oort cloud exists, it marks the true edge of the Sun's gravitational influence. A distant halo of icy wanderers. Io is the most volcanic world in the solar system. Jupiter's moon, Io, is a seething, restless world covered in active volcanoes. Its surface is constantly reshaped by eruptions of molten sulfur and rock, painting the landscape in vivid yellows, reds, and blacks. Some volcanic plumes rise hundreds of kilometers into space. This extreme activity is driven by tidal heating. Io is squeezed and stretched by Jupiter's gravity, along with gravitational tugs from neighboring moons. The friction from this constant flexing heats the interior, powering its furious geology. Unlike Earth's cooling crust, Io's surface is young, volatile, and ever-changing. A lava-lit moon with a molten heart, Triton orbits backward around Neptune. Triton, Neptune's largest moon, is unique among large moons because it orbits its planet in the opposite direction of Neptune's rotation, a motion called retrograde orbit. This backward path suggests Triton did not form alongside Neptune, but was likely captured from the Kuiper belt. That capture may have caused dramatic upheaval, potentially disrupting Neptune's original satellite system. Triton is also geologically active, with cryovolcanoes that spew icy material into space and a thin atmosphere that drifts in and out with the seasons, cold, distant, and moving in reverse. Triton is a world that defies expectations at every turn. Earth's moon is unusually large. Compared to the size of its host planet, Earth's moon is enormous. No other rocky planet in the solar system has such a relatively large satellite. In fact, the moon is about 1/4 the diameter of Earth, a ratio more typical of dwarf planet moon systems than full-sized planets. Most scientists believe the moon formed after a marsed body collided with the young Earth, ejecting debris into orbit that eventually coalesced into the moon. This close partnership has profoundly influenced Earth's tides, climate, and stability over billions of years. Our moon is not just a companion. It is a cosmic legacy of planetary collision and renewal. Planetary orbits are not perfect circles. Although we often imagine the planets moving in perfect circular paths around the Sun, their orbits are actually ellipses, slightly stretched circles with the Sun offset from the center. This elliptical shape means that each planet has a point where it is closest to the Sun, called perihelion, and a point where it is farthest, called aphelion. For most planets, the difference is subtle, but for others, like Mercury and Pluto, it is more dramatic. These variations influence seasons, solar radiation, and orbital speed. The elliptical nature of planetary motion was first described by Johannes Kepler in the 1600s, reshaping our understanding of the solar system's elegant mechanics. Some comets come from the edge of interstellar space. Long-period comets, the kind that appear only once every few thousand years, are believed to come from the Oort cloud, a distant shell of icy debris that may lie nearly a light year from the Sun. These comets travel on elongated, loosely bound orbits and are often dislodged from their resting places by passing stars or galactic tides. When they fall inward toward the Sun, they can light up with spectacular tails, visible even from Earth. Some may have spent billions of years drifting in darkness before being nudged into motion. Their bright returns are fleeting glimpses of the solar system's most ancient untouched matter. The Sun will become a white dwarf. The Sun, like all stars, has a finite lifetime. At about 5 billion years, it will exhaust the hydrogen fuel in its core and expand into a red giant, engulfing the inner planets. After shedding its outer layers in a glowing shell of gas called a planetary nebula, the core that remains will become a white dwarf, a dense Earth-sized remnant made mostly of carbon and oxygen. This white dwarf will no longer produce energy, but will slowly cool over trillions of years. It will be the final form of our sun, a glowing ember in the darkness, marking the end of its stellar journey. Mars has seasons like Earth, though it is colder and thinner in atmosphere. Mars experiences seasons much like our own planet. This is because Mars has a similar axial tilt, about 25 degrees compared to Earth's 23, as it orbits the Sun. This tilt causes sunlight to strike different hemispheres more directly at different times of year. The result is a cycle of spring, summer, autumn, and winter with varying temperatures and light. Martian seasons also influence polar ice caps, dust storms, and even subtle changes in air pressure. They unfold more slowly than on Earth, however, because Mars takes nearly twice as long to complete a year. Ganymede is the largest moon in the solar system. Jupiter's moon Ganymede is the largest natural satellite in the solar system, even bigger than the planet Mercury. With a diameter of over 5,000 kilometers, Ganymede has a rocky core, a possible subsurface ocean, and a crust covered in ridged ice and ancient scars. Uniquely, it is the only moon known to have its own magnetic field, which creates shimmering auroras in its thin atmosphere. Scientists believe Ganymede may have multiple layers of oceans sandwiched between sheets of ice, forming a complex internal world. Despite its size and richness, it remains quiet and dark, orbiting deep within Jupiter's magnetic grasp. Pluto sometimes orbits closer to the Sun than Neptune. Although Pluto is usually the most distant of the classical planets or dwarf planets, its orbit is highly elliptical, meaning it sometimes travels closer to the Sun than Neptune. This last occurred between 1979 and 1999, when Pluto was temporarily the 8th planet from the Sun instead of the 9th. Even so, the two worlds never collide or come dangerously close because their orbits are in resonance. For every 3 orbits Neptune makes, Pluto completes exactly 2. This gravitational choreography keeps them in a stable dance, with their paths never crossing. It is a delicate balance, governed by celestial rhythm and time. The Sun reverses its magnetic field every 11 years. Roughly every 11 Earth years, the Sun's magnetic field flips. The north and south magnetic poles switch places. This process, known as the solar magnetic cycle, is tied to the Sun's internal dynamics and affects solar activity, including sunspots, flares, and coronal mass ejections. At the peak of the cycle, called solar maximum, the Sun is more active, with more intense radiation and magnetic storms. As the cycle wanes, activity decreases, eventually reaching solar minimum. These cycles influence Earth's upper atmosphere, satellites, and even auroras. The Sun's magnetism is not fixed, but pulses and flows like a breathing magnetic heartbeat. Planetary alignments do not cause natural disasters. It is a common myth that planetary alignments can trigger earthquakes, floods, or other major disasters on Earth. But there is no scientific evidence for such effects. The gravitational pull of other planets on Earth is minuscule compared to the Moon or the Sun. Even during rare alignments, their combined influence is negligible. The Moon, being so close, has far more impact on tides and seismic stress than massive but distant planets like Jupiter or Saturn. Planetary alignments are beautiful and mathematically interesting, but they are gravitationally harmless. A silent dance of distant worlds, not a celestial omen. Leaving the solar system takes decades. Escaping the pull of the Sun is no small task. Spacecraft like Voyager 1 and 2 launched in the 1970s, have only recently entered interstellar space. The region beyond the heliopause, where the solar wind gives way to the interstellar medium. These missions took more than 40 years to reach that boundary, traveling outward at speeds over 60,000 kilometers per hour. The Voyager probes have crossed the orbits of the planets, passed through the Kuiper Belt, and continued into the dark. They carry instruments still functioning, as well as a golden record filled with sounds of Earth. They are our quiet ambassadors to the galaxy. Earth's magnetic field shields us from space radiation. Surrounding our planet is an invisible magnetic field generated by the movement of molten iron in Earth's outer core. This magnetic field deflects charged particles from the Sun, protecting the atmosphere and surface from harmful solar and cosmic radiation. Without it, the solar wind would gradually erode our atmosphere as it likely did on Mars. The field also funnels some particles toward the poles where they interact with atmospheric gases and produce auroras, shimmering curtains of green, red, and violet light. Earth's magnetosphere is a dynamic shield, essential for preserving both life and climate over geological time. The Moon is slowly moving away from Earth. Each year, the Moon drifts about 3.8 centimeters farther from Earth. This slow retreat is caused by tidal interactions. The gravitational pull between Earth and the Moon creates bulges in our planet's oceans, which in turn push the Moon slightly outward. In the distant past, the Moon was much closer and appeared significantly larger in the sky. As it recedes, our days gradually lengthen, and eclipses become less frequent and dramatic. Billions of years from now, the Moon's orbit will be so wide that total solar eclipses will no longer be possible. The sky is changing, even if we do not yet feel it. The Kuiper Belt holds icy worlds with mirrored surfaces. Far beyond Neptune, the Kuiper Belt contains not only dwarf planets, but also smaller icy bodies with startlingly bright surfaces. One example is Haumea, a fast-spinning football-shaped object coated in crystalline water ice. Another, Eris, reflects nearly all the sunlight that hits it, making it one of the most reflective bodies in the solar system, brighter than freshly fallen snow. These objects may have been resurfaced by cryovolcanism, impacts, or chemical interactions. In the darkness at the edge of the Sun's reach, some of these distant worlds gleam like cold mirrors, catching faint sunlight in their frozen silence. Enceladus sprays water into space. Saturn's tiny moon, Enceladus, may be small, but it hides a spectacular secret. From its south pole, towering geysers of water vapor and ice crystals erupt into space through cracks known as tiger stripes. These plumes are powered by tidal heating beneath the surface, where friction caused by Saturn's gravitational pull keeps a subsurface ocean in a liquid state. The material in the plumes contains organic compounds, salts, and even signs of hydrothermal activity, raising the tantalizing possibility of life. Some of the water escapes into space and helps replenish Saturn's earring, creating a living connection between moon and planet. Some asteroids are just piles of rubble. Not all asteroids are solid rock. Many are loose collections of stones, gravel, and dust held together only by gravity, structures known as rubble piles. These fragile bodies can form after collisions shatter larger asteroids, with the debris slowly coming back together over time. Rubble pile asteroids can have large internal voids, spin strangely, and change shape under pressure. Missions like Hayabusa 2 and OSIRIS-REx have visited such bodies, confirming their delicate, porous nature. These asteroids are not monolithic relics, but chaotic assemblages. ancient drifting ruins of early planetary construction that barely hold themselves together as they orbit the Sun. Mercury's core is disproportionately large. Mercury is a small planet, but it has an unusually massive iron core. This metallic center makes up about 80% of the planet's radius, a far larger proportion than seen in Earth or Venus. The reason for this oversized core remains uncertain. Some scientists think Mercury once had a thick, rocky mantle that was stripped away by a giant impact. Others believe it formed close to the Sun, where solar forces favored the accumulation of heavier elements. The result is a planet with a thin crust, a huge core, and a weak magnetic field. A metal-heavy survivor from the solar system's chaotic youth. Venus has no moons at all. Among the rocky planets, only Mercury and Venus are without natural satellites. While Mercury's proximity to the Sun may explain its lack of moons, Venus's situation is more puzzling. It is roughly the same size as Earth, which has a large moon, yet Venus has none. Some theories suggest it may have once had a moon that fell back into the planet or was lost in a collision. Others argue that Venus's slow, retrograde rotation might prevent stable orbits from forming. Whatever the cause, Venus orbits alone. A bright cloud-wrapped world with no lunar companion in its twilight sky. Most of the solar system's moons orbit gas giants, while Earth has just one moon, and Mars has two tiny ones. The giant planets of the outer solar system are surrounded by sprawling systems of satellites. Jupiter and Saturn each have dozens of confirmed moons, ranging from tiny captured asteroids to massive worlds like Ganymede and Titan. Uranus and Neptune also host many icy moons, some with complex orbits and hidden oceans. These gas giants act like miniature solar systems, their gravity drawing in debris and coalescing satellites over time. The farther from the Sun you go, the more moons you will find. A reminder that gravity gathers companions in the cold. Hubble has photographed planets from Earth orbit. Though it orbits just above Earth, the Hubble Space Telescope has captured detailed images of the outer planets, including cloud bands on Jupiter, storms on Neptune, and seasonal changes on Mars. These images provide long-term observations that complement spacecraft flybys, offering views of evolving weather patterns, ring systems, and planetary auroras. Hubble's clarity allows scientists to track storm development, monitor impact events, and study atmospheres in ultraviolet and visible light. From its quiet perch in low Earth orbit, Hubble watches not only the distant galaxies, but also the shifting faces of our neighboring worlds. Jupiter's Great Red Spot is centuries old. The Great Red Spot is a massive storm swirling in Jupiter's southern hemisphere, wide enough to swallow 2 or even 3 Earths. It has been raging for at least 350 years, possibly much longer. First observed in the 1600s through early telescopes, the storm has changed over time, gradually shrinking, but still remaining powerful. Its reddish hue may be caused by complex chemical reactions in Jupiter's atmosphere, triggered by sunlight and high-altitude compounds. Wind speeds exceed 400 kilometers per hour along its outer edges. While Earth's storms last days or weeks, this Jovian tempest spans centuries. Trapped in the planet's turbulent belts, Neptune radiates more heat than it receives from the Sun. Although it lies far from the Sun, Neptune is not a frozen, inert world. In fact, it radiates about 2.6 times more energy than it receives. This internal heat drives strong winds and storm systems, including the fastest recorded winds in the solar system. The exact source of Neptune's heat remains uncertain. but possibilities include residual energy from its formation, slow gravitational contraction, or radioactive decay within its core. Despite its extreme distance, Neptune is a world of Earth is the only planet with water in all three states. Our planet is unique in that water exists naturally on its surface as a solid, liquid, and gas. Ice caps and glaciers, oceans and lakes, clouds and vapor all coexist and cycle through the atmosphere, land, and sea. This balance is crucial for life and is regulated by Earth's distance from the Sun, its atmospheric pressure, and its relatively stable climate. Other worlds may have water in isolated forms, icy crusts, vapor in thin atmospheres, or hidden subsurface oceans, but none show the same dynamic planet-wide presence. On Earth, water flows, freezes, and evaporates in a never-ending life-sustaining dance. The heliopause marks the edge of the Sun's influence. As the solar wind flows outward from the Sun, it eventually collides with the interstellar medium, the thin gas and dust between stars. This boundary is called the heliopause, and it defines the outer edge of the Sun's protective bubble known as the heliosphere. Beyond this point, the pressure from other stars and galactic particles becomes stronger than the solar wind. Voyager 1 crossed the heliopause in 2012, followed by Voyager 2 in 2018, entering true interstellar space. Though the Sun's gravity still extends much farther, the heliopause marks the end of its energetic reach, the final breath of solar influence before deep space begins. The solar system is drifting through a local cloud. Our entire solar system is moving through a region of space called the local interstellar cloud, a thin concentration of gas and dust about 30 light-years across. It is part of a larger structure known as the local bubble, formed by ancient supernova explosions. As the Sun travels through this cloud at about 7,000 kilometers per hour, its heliosphere acts like a shield, deflecting interstellar material. Scientists study this cloud to understand how interstellar conditions can affect cosmic rays, the heliosphere's shape, and even climate on Earth. We are not sitting still in space. We are sailing slowly and silently through a galactic fog. Some moons are geologically active. Activity is not limited to planets. Several moons in the solar system show signs of internal energy and surface change. Io, a moon of Jupiter, is riddled with active volcanoes fueled by tidal heating. Enceladus, orbiting Saturn, vents plumes of water vapor into space. Europa and Ganymede likely have subsurface oceans stirred by internal warmth. Even distant Triton, Neptune's captured moon, shows signs of cryovolcanism. Icy eruptions driven by shifting pressures below. These moons are not static ice balls. They are restless worlds with geology, chemistry, and perhaps even the potential for biology hidden beneath their frozen exteriors. Pluto's atmosphere comes and goes. Though Pluto is small and cold, it has a thin atmosphere composed mostly of nitrogen with traces of methane and carbon monoxide. When Pluto approaches the Sun in its elliptical orbit, surface ices sublimate into gas, forming a hazy envelope that expands into space. But as it moves farther out, the atmosphere cools and collapses, freezing back onto the surface like frost. This cycle repeats over Pluto's 248-year orbit. During the New Horizons flyby in 2015, Pluto's atmosphere was visible as a layered blue haze, a fleeting breath of warmth around a world that spends most of its time in deep cosmic winter. Temperatures at the Sun's core exceed 15 million degrees. Deep inside the Sun, At its center, temperatures soar to over 15 million degrees Celsius. Here, hydrogen atoms are compressed under immense pressure until they fuse into helium, releasing enormous amounts of energy in the process. This fusion is what powers the sun's light and heat, and ultimately all life on Earth. The energy generated in the core takes hundreds of thousands of years to reach the surface, bouncing through layers of dense plasma. Once it escapes, it travels across space in just over 8 minutes to reach us. The sun's radiant calm hides an unimaginably hot and violent heart. Uranus has a faint tilted ring system. Though Saturn's rings are the most iconic, Uranus also has rings, 13 known ones in fact, though they are much darker and fainter. Made of tiny particles of rock and ice, these rings orbit in alignment with Uranus's unusual tilt. Since the planet lies almost on its side, the rings appear vertical when viewed from above the sun's north pole. Some of the rings are narrow and sharp-edged, possibly shaped by small moons that shepherd their structure. They were not discovered until 1977, when they blocked the light of a background star. They are subtle, shadowy bands circling a sideways planet. The heliosphere is a magnetic bubble blown by the sun. The solar wind, a stream of charged particles released by the sun, flows outward in all directions, forming a vast magnetic bubble around the entire solar system. This structure is called the heliosphere, and it acts like a shield against galactic radiation. Shaped by solar activity and interstellar pressure, it stretches far beyond Pluto, enclosing the planets, comets, and distant objects. Its outer edge, the heliopause, is where solar influence fades. As the sun orbits the Milky Way, the heliosphere moves with it, protecting the solar system as it drifts through changing regions of interstellar space. Mercury's orbit helped prove Einstein's theory of gravity. For centuries, astronomers noticed something strange about Mercury's orbit. Its closest approach to the sun, called perihelion, slowly shifted over time, more than Newtonian physics could account for. In 1915, Albert Einstein's theory of general relativity provided the solution. According to relativity, massive objects like the sun warp the fabric of space-time, subtly altering planetary paths. The small but measurable effect on Mercury's orbit matched Einstein's predictions exactly. This became one of the first experimental confirmations of his revolutionary theory and a quiet triumph of mathematics, explaining a quirk in the motion of a scorched rocky world. The moon shapes Earth's tides. The daily rise and fall of ocean tides on Earth are largely caused by the gravitational pull of the moon. As the moon's gravity tugs on Earth's oceans, it creates bulges on the side facing the moon and the opposite side. As Earth rotates, these bulges move across the globe, producing high and low tides. The sun also influences tides, creating spring and neap tides depending on its alignment with the moon. Tidal forces not only affect oceans, but can also subtly shift the Earth's crust and even influence the rotation of the planet itself. The moon's silent pull keeps the oceans in motion. There may be undiscovered planets beyond Neptune. Astronomers have noticed that some distant objects in the Kuiper belt follow clustered, elongated orbits that cannot be easily explained by the known planets. One leading theory is that a large, as-yet-undetected planet, sometimes called Planet 9, may be influencing these distant paths with its gravity. If it exists, this hidden planet would be several times the mass of Earth and orbit far beyond Pluto, taking thousands of years to complete a single revolution. No direct evidence has yet confirmed it, but telescopes are searching. If found, It would reshape our understanding of the solar system's outer architecture. Callisto may have an ocean beneath its icy surface. Jupiter's moon, Callisto, appears quiet and cratered, with an ancient surface untouched by recent geological activity. But deep beneath that frozen crust, scientists suspect a subsurface ocean may exist, kept liquid by internal heating and perhaps residual heat from formation. Magnetic readings from the Galileo spacecraft hinted at a conductive layer beneath the surface consistent with salty water. If confirmed, Callisto would join Europa and Ganymede as another ocean world. Though less well known, Callisto's deep, dark sea could contain ingredients for life, silently sealed beneath a shell of ice and time. Venus is hotter than Mercury despite being farther from the Sun. Although Mercury is the closest planet to the Sun, Venus holds the record for the hottest surface temperatures. This is due to its incredibly thick atmosphere, composed mostly of carbon dioxide, which traps heat in a runaway greenhouse effect. Surface temperatures on Venus exceed 460 degrees Celsius, hot enough to melt lead. The dense clouds reflect sunlight, but they also prevent heat from escaping. Meanwhile, Mercury, with its thin exosphere, has no such insulation and cools rapidly on its dark side. Venus's searing heat is not just about proximity to the Sun. It is about atmosphere and the power of trapped radiation. The rings of Saturn are made mostly of ice, though they shimmer like solid bands. Saturn's rings are composed of countless individual particles, mostly water ice, ranging from grains of dust to chunks the size of houses. These icy fragments orbit in an incredibly thin, flat disk, kept in place by Saturn's gravity and the influence of nearby moons. The ice gives the rings their brilliant reflectivity, making them one of the brightest features in the solar system when seen from afar. Embedded within the rings are narrow gaps, wave patterns, and ringlets shaped by gravitational resonances. The rings are dynamic, ever-changing structures of sculpted ice caught in motion. Ceres is both an asteroid and a dwarf planet. Located in the asteroid belt between Mars and Jupiter, Ceres is the largest object in that region. So large, in fact, that it qualifies as a dwarf planet. Discovered in 1801, Ceres is spherical, unlike smaller asteroids, and may contain a subsurface layer of briny water or mud. NASA's Dawn spacecraft revealed mysterious bright spots on its surface, which turned out to be deposits of salt, possibly left behind by evaporating water. Ceres is a hybrid world, neither quite planet nor typical asteroid, offering a glimpse into the early ingredients of planetary formation. Mars appears red because of rust. The surface of Mars is coated in a fine dust of iron oxide, the same compound that gives rust its color. Over billions of years, this iron-rich material has oxidized in the thin Martian atmosphere, creating the planet's signature reddish hue. The dust is so pervasive that it colors the sky during storms and coats the entire planet. Despite the rusty appearance, Mars also has dark basaltic plains and polar ice caps, creating subtle color variations across its surface. But from a distance, that distinctive reddish tone dominates, a dusty signal of oxidation on a cold desert world. Sunspots are cooler regions on the Sun's surface. Though the Sun's surface blazes at thousands of degrees, some areas appear darker. Not because they are cold, but because they are cooler than their surroundings. These are sunspots, temporary regions where intense magnetic activity suppresses the outward flow of heat. Sunspots can be larger than Earth and often appear in pairs or clusters. They follow an 11-year cycle, growing more numerous and active as the Sun approaches solar maximum. Despite their name, they are still extremely hot, thousands of degrees, but the contrast makes them appear dark. These spots are magnetic scars, revealing the sun's ever-changing internal rhythms. Uranus was discovered by a telescope. Unlike the planets visible since ancient times, Uranus was not officially identified until 1781, when astronomer William Herschel observed it through a telescope. At first he thought it might be a comet or star, but further observations confirmed its planetary motion. Uranus became the first planet discovered in modern times, expanding the known boundaries of the solar system. Its discovery marked a shift from naked-eye astronomy to instrument-based exploration. Since then, Uranus has revealed many surprises, from its extreme axial tilt to its faint rings and icy moons. It is a planet that quietly rewrote the map of the night sky. The solar system is about 4.6 billion years old. By studying ancient meteorites, radioactive isotopes, and the oldest rocks on Earth and the Moon, scientists have traced the age of the solar system to around 4.6 billion years. It began as a swirling cloud of gas and dust, a solar nebula which collapsed under its own gravity, forming the Sun at its center. The remaining material coalesced into planets, moons, asteroids, and comets. This process of accretion and differentiation laid the foundation for everything that followed. The planets we see today are survivors of a chaotic beginning shaped by collisions, migrations, and long, slow cooling. Vesta has a layered structure like a planet. Vesta, the second largest object in the asteroid belt, is not just a rock. It is a protoplanet with differentiated layers. Beneath its surface lies a mantle and a dense metallic core, similar to the internal structure of Earth and other terrestrial planets. This means Vesta once had enough internal heat to melt and separate into layers, a process called planetary differentiation. The giant impact that carved out the Rhea Silvia crater at its south pole may have exposed some of these deeper layers. Vesta is a frozen fossil, a planetary building block that never quite made it to full planet status. The Moon has quakes. Though it appears still and silent, the Moon occasionally trembles. These moonquakes can be caused by tidal forces from Earth's gravity, thermal expansion as the lunar surface heats and cools, or even meteorite impacts. Some quakes originate deep within the Moon and can last for up to an hour, far longer than earthquakes on Earth. Data from the Apollo missions first revealed these subtle shakes, and new instruments continued to study them. Though the Moon has no tectonic plates, its quakes suggest an interior that is not entirely dormant. A solid world with a quiet, pulsing heart. Triton is a captured moon. Neptune's largest moon, Triton, is unique among major moons because it orbits in the opposite direction of its planet's rotation, a retrograde orbit. This unusual path suggests that Triton did not form around Neptune, but was captured from the Kuiper belt long ago. The gravitational disruption from this capture may have destroyed Neptune's original moons and tilted Triton's own interior, causing tidal heating. Today, Triton has geysers that spew nitrogen into space, a thin atmosphere and a frozen surface marked by strange cantaloupe-like textures. It is both a relic of the outer solar system and a moon shaped by a violent adoption. Neptune has 14 known moons. Neptune, the farthest major planet from the Sun, is orbited by at least 14 moons, ranging from large and mysterious to small and irregular. The largest, Triton, makes up most of the mass, but others like Proteus, Naiad, and Larissa follow eccentric and varied paths. Some are likely captured Kuiper belt objects, while others may have formed from collisions or debris. Most of these moons are icy and dark, reflecting very little sunlight. Their orbits offer clues about Neptune's violent past and possible planetary migrations. Together, they form a scattered family of companions around a planet that drifts on the solar system's distant edge. The Parker Solar Probe is touching the Sun. Launched in 2018, NASA's Parker Solar Probe is the first spacecraft to fly directly into the Sun's outer atmosphere, known as the corona. It moves at extraordinary speeds, faster than any object ever built, and endures temperatures of over 1,000 degrees Celsius. Protected by a carbon composite heat shield, the probe dips closer with each orbit, gathering data on solar wind, magnetic fields, and energetic particles. Its mission is to solve long-standing mysteries, like why the corona is hotter than the Sun's surface and how solar flares accelerate. In a sense, it is not just studying the Sun, it is flying through it. Some meteorites on Earth came from Mars, though Mars is millions of kilometers away. Pieces of it have landed on Earth. These are Martian meteorites. Fragments of rock blasted off the surface by powerful impacts, which then traveled through space and eventually fell into our atmosphere. Scientists identify them by comparing their chemical makeup to data collected by Mars rovers and orbiters. Some of these meteorites contain tiny bubbles of trapped Martian air and minerals shaped by water, offering direct clues to Mars's geological and chemical history. These wayward stones are samples from another world, sent to us by nature long before any spacecraft returned the favor. The Sun is mostly hydrogen and helium. About 70% of the Sun's mass is hydrogen, and most of the rest is helium. These two lightest elements dominate its makeup and fuel the nuclear fusion at its core. Under extreme pressure and heat, hydrogen atoms are fused into helium, releasing vast amounts of energy. The remaining 1 to 2% of the Sun's mass includes oxygen, carbon, nitrogen, and heavier elements, all of which originated in earlier generations of stars. Despite its brilliance and complexity, the Sun is fundamentally simple in composition. A glowing sphere of primordial gases shaped by gravity and nuclear fire. Earth's tilt gives us seasons. Earth's axis is tilted about 23.5 degrees relative to its orbit around the Sun. This tilt is the reason we experience seasons. When one hemisphere is tilted toward the Sun, it receives more direct sunlight and longer days, resulting in summer. When tilted away, the sunlight is weaker and days are shorter, bringing winter. Without this tilt, seasons would barely exist, and most of Earth's climates would be far more uniform. The tilt has shifted slightly over time due to gravitational influences from the Moon and other planets, but it remains one of the quiet architects of life's seasonal rhythms. Jupiter's magnetosphere is the largest structure in the solar system. Jupiter's immense magnetic field extends millions of kilometers into space, forming a magnetosphere so vast it would appear larger than the Sun in the night sky if it were visible. This field is powered by electric currents in the planet's metallic hydrogen interior. Within the magnetosphere, charged particles zip along magnetic lines, creating intense radiation belts, massive auroras, and fierce electrical storms. The field captures particles from Io's volcanic eruptions and shapes the orbits of nearby moons. For spacecraft, the radiation here is a major hazard. For scientists, it is a laboratory for studying planetary magnetism at its most extreme. The asteroid belt may have been prevented from forming a planet. Between Mars and Jupiter lies the asteroid belt, a wide region filled with rocky debris. Scientists believe that the material here might once have coalesced into a planet, but Jupiter's immense gravity disrupted the process. Instead of forming into a single world, the fragments remained scattered. Collisions, resonances, and gravitational tugs kept the region stirred and unstable, preventing planetary growth. The result is a belt of countless asteroids, from tiny pebbles to bodies hundreds of kilometers across. It is a graveyard of unfulfilled potential, a region where a planet almost was. Venus is shrouded in sulfuric acid clouds. The thick atmosphere of Venus is not only heavy with carbon dioxide, but also layered with clouds of sulfuric acid droplets. These clouds reflect most of the sunlight, making Venus one of the brightest objects in Earth's sky. The acid rains from these clouds never reach the surface, as the heat evaporates them before they fall. Instead, the clouds circulate, producing storms and lightning in a toxic shroud. They trap heat, making the planet's surface hotter than Mercury, despite its greater distance from the Sun. Venus is a dazzling and deadly world, wrapped in a corrosive veil. Jupiter's moon Europa may glow in the dark. Observations suggest that Europa's icy surface might emit a faint glow at night, caused by radiation from Jupiter's powerful magnetic field interacting with its ice. Laboratory experiments show that salty ice exposed to radiation can emit visible light. If so, Europa's surface could softly glow even on its night side, painting an eerie luminous landscape. This glow might reveal clues about the moon's composition and chemistry, as different salts glow with different colors. Europa's radiant ice could be more than beautiful. It could be a tool for future explorers to study the hidden ocean beneath. Comets are frozen time capsules. Comets are made of ice, dust, and rock, remnants from the solar system's earliest days. When they travel inward from the cold outer regions, sunlight warms them, releasing gas and dust that form glowing tails stretching across space. These tails always point away from the sun, pushed by solar wind and radiation. Comets often carry complex organic molecules, and many scientists believe they may have delivered water and ingredients for life to early Earth. Every comet is a frozen time capsule, preserving ancient material from the dawn of the planets. Awakening only when stirred by the sun. Mars's thin atmosphere cannot protect liquid water. Today, Mars has an atmosphere less than 1% as dense as Earth's. This means that liquid water cannot remain stable on its surface. It would quickly evaporate or freeze. In the past, Mars likely had a thicker atmosphere and abundant surface water, as suggested by dried river valleys, deltas, and minerals formed in wet conditions. But over time, solar winds stripped much of the atmosphere away, leaving the planet cold and arid. What water remains is mostly frozen in polar ice caps or locked underground. Mars is a desert world where rivers once ran but no longer flow. Some moons are almost as complex as planets. Titan, Europa, and Ganymede are moons, yet they rival planets in size and geology. Titan has thick clouds, methane lakes, and a rich atmosphere. Europa hides a subsurface ocean beneath its cracked, icy shell. Ganymede has magnetic fields and multiple ocean layers. Even smaller moons like Enceladus and Io show active geology. These moons challenge the idea that only planets are dynamic worlds. They prove that satellites, too, can hold oceans. Weather, magnetism, and heat, making them as fascinating as the planets they orbit. In the solar system, moons are not mere companions. They are worlds in their own right. The solar wind shapes planetary atmospheres. the Sun constantly emits a stream of charged particles known as the solar wind. As this wind sweeps across the solar system, it collides with planets, moons, and magnetic fields. On Earth, the magnetosphere deflects it, producing a rock. On Mars, without such protection, the solar wind erodes the atmosphere directly. On comets, it blows away dust and gas, shaping their glowing tails. Even the heliosphere itself, the vast bubble around the solar system, is sculpted by the solar wind pushing outward against interstellar space. It is a constant breath of the Sun, reshaping everything it touches. The Moon keeps Earth's axis stable. Earth's tilt of 23.5 degrees gives us seasons, but it is the Moon that keeps that tilt steady. Without the Moon's gravitational influence, Earth's axis could wobble chaotically over millions of years, swinging between extreme tilts. Such shifts would cause wild climate swings, destabilizing ecosystems and possibly hindering the evolution of complex life. The Moon acts like a stabilizing weight, keeping Earth's spin balanced. In this way, the Moon has been more than a companion in the sky. It has been a guardian of Earth's climate stability across the ages. Meteor showers come from comet dust. Each year, Earth passes through streams of dust left behind by comets. As these tiny particles hit our atmosphere at high speeds, they burn up, creating streaks of light across the sky. These meteor showers, like the Perseids in August or the Geminids in December, are predictable annual events tied to Earth's orbit. Some showers can produce dozens or even hundreds of meteors per hour. Though the particles are often no bigger than grains of sand, they light up the sky as fiery trails. They are reminders that Earth is constantly moving through a cosmic rain of comet dust. Saturn is less dense than water. If you could find an ocean big enough, Saturn would float. Its average density is about 0.7 grams per cubic centimeter, less than water. Despite its immense size and gravity, Saturn is mostly hydrogen and helium, making it lightweight for its volume. This low density gives it a puffy appearance and contributes to its rapid rotation, which flattens the planet at the poles and bulges it at the equator. Saturn is a giant of gas, airy and buoyant compared to rocky worlds. A colossal planet that, by density alone, could float in an impossible cosmic sea. Some asteroids are metallic. While many asteroids are rocky or carbon-rich, others are composed largely of metal, particularly iron and nickel. These metallic asteroids are thought to be remnants of the cores of shattered protoplanets, exposed after collisions stripped away their outer layers. One of the most famous is Psyche, an asteroid about 220 kilometers across, which may represent the exposed core of an ancient failed planet. NASA is sending a mission to explore Psyche, hoping to learn more about planetary interiors and the building blocks of terrestrial planets. These metallic wanderers are fragments of broken worlds, shining with the metals of lost beginnings. The solar system has regions called Lagrange points. These are positions in space where the gravitational pull of two large bodies, like Earth and the Sun, balance with the centrifugal force of an orbiting object. At these spots, a satellite can stay in a stable position relative to both bodies. There are 5 such points in the Earth-Sun system, labeled L1 through L5. Some, like L4 and L5, are especially stable and can collect asteroids known as Trojans. Spacecraft like the James Webb Space Telescope orbit near L2, using the stable balance to remain in place with minimal fuel. Lagrange points are cosmic parking spots shaped by gravity's delicate geometry. Some moons may have atmospheres, While most moons are airless, a few have thin or significant atmospheres. Titan has a thick, nitrogen-rich atmosphere with clouds, storms, and methane rain. Triton has a tenuous nitrogen atmosphere that changes with the seasons. Even our moon has an extremely thin exosphere, made of trace gases like helium and sodium. These atmospheres, though fragile or rare, show that moons can host weather, winds, and chemical cycles, much like planets. Each atmosphere is unique, a fleeting veil draped over a satellite, shaped by gravity, chemistry, and distance from the sun. Mars once had a magnetic field. Billions of years ago, Mars had a global magnetic field similar to Earth's, created by motion in its molten core. This shield protected its atmosphere from the solar wind, allowing water to exist on the surface. But the Martian core cooled and solidified, shutting down the dynamo effect. Without its magnetic field, the atmosphere was gradually stripped away by solar radiation, transforming Mars from a warmer, wetter planet into the cold desert it is today. Ancient rocks preserve traces of this long-lost field, magnetic fossils of a time when Mars was more alive. The Sun is an ordinary star, though it is the center of our lives and the most familiar star in the universe. The Sun is not special by cosmic standards. It is a G-type main sequence star, one of hundreds of billions in the Milky Way. Stars larger, hotter, and brighter exist in abundance, as do stars smaller, cooler, and dimmer. What makes the Sun unique is its stability. It has shone steadily for billions of years, providing a reliable source of energy for life. To the galaxy, it is just another star. To us, it is everything. Asteroids sometimes collide with Earth. Throughout Earth's history, impacts from asteroids and comets have shaped our planet's surface and history. The most famous is the impact that contributed to the extinction of the dinosaurs 66 million years ago, leaving the Chicxulub crater in Mexico. Smaller impacts occur more often, burning up in the atmosphere or creating local damage. Space agencies track near-Earth objects to assess risks and prepare potential deflection strategies. Though large impacts are rare, they are inevitable over long time spans. Earth carries the scars of cosmic collisions, reminders that space is not an empty void, but a place of drifting hazards. Neptune has dark storms. Like Jupiter's great red spot, Neptune has its own storm systems, vast swirling tempests that appear as dark patches against its blue atmosphere. These storms can be as large as Earth and last for years, though they eventually dissipate and reappear in new locations. Unlike Jupiter's storms, which are long-lived, Neptune's seem more transient. They are powered by internal heat rising through the atmosphere, creating turbulence in methane-rich clouds. These storms reveal Neptune's restless climate, where supersonic winds and shifting currents constantly reshape its face. Even at the solar system's edge, where the rages on, Earth has auroras at both poles. When charged particles from the solar wind interact with Earth's magnetic field, they are funneled toward the poles, where they collide with atmospheric gases and create shimmering curtains of light. In the northern hemisphere, these displays are called the aurora borealis, or northern lights. In the south, they are the aurora australis. Colors range from green and red to blue and violet, depending on which gases are excited. Auroras are not unique to Earth. They also occur on Jupiter, Saturn, and even Uranus, glowing where magnetic fields guide solar energy into planetary skies. The solar system is tilted relative to the galaxy. Our planets orbit the Sun in a relatively flat disk called the ecliptic plane. But this plane is not aligned with the Milky Way's galactic plane. Instead, it is tilted by about 60 degrees. This means when we look up at the Milky Way in the night sky, we are not looking along the same plane as the solar system's orbits, but across them at an angle. This tilt likely results from the chaotic conditions of the solar system's birth and the influence of nearby stars and clouds in the galaxy. We orbit the Sun, tilted within a tilted galaxy. Earth's magnetic poles drift. The magnetic north and south poles of Earth are not fixed points. They wander slowly across the surface due to shifts in the flow of molten iron in Earth's outer core. In recent decades, the North Magnetic Pole has been moving faster, drifting from Canada toward Siberia at tens of kilometers per year. These shifts can affect navigation systems, compasses, and even animal migrations that rely on Earth's magnetic field, though the field itself occasionally weakens and reverses over geologic time. The slow wandering poles remind us that even Earth's magnetic shield is alive and in motion. Solar eclipses are fleeting coincidences. A total solar eclipse occurs when the Moon passes directly between Earth and the Sun, perfectly covering the Sun's disk. This is possible because the Sun is about 400 times wider than the Moon, but also about 400 times farther away, making them appear nearly the same size in the sky. But the Moon is slowly moving away from Earth. In a few 100 million years, it will appear too small to fully cover the Sun, and total eclipses will cease. Today's eclipses are a temporary alignment, a cosmic coincidence that future worlds will never see. The planets formed from a protoplanetary disk. About 4.6 billion years ago, the solar system began as a swirling disk of gas and dust surrounding the young Sun. Within this protoplanetary disk, particles collided and stuck together, gradually building up into planetesimals, then protoplanets, and finally the full-size planets we know today. Closer to the Sun, only metals and rocks could survive the heat, forming the terrestrial planets. Farther out, Isas and gases coalesced into the giant planets. The asteroid belt and Kuiper belt are leftover fragments that never fully formed into worlds. The planets are children of dust, born from the same nebula that gave rise to the Sun. Some asteroids are active like comets. Though asteroids are usually thought of as dry, rocky bodies, a small number show comet-like activity, releasing dust and gas tails as they orbit the Sun. These objects, called active asteroids or main belt comets, blur the line between the two categories. They may contain hidden ice that sublimates when heated or eject dust from collisions. Their dual nature suggests that water and organics may be more widely distributed in the solar system than once thought. Active asteroids are rare but important, linking the rocky inner worlds with the icy outer regions. Jupiter protects Earth from many comets. Because of its immense gravity, Jupiter acts as a cosmic shield for the inner planets. It can capture or redirect comets and asteroids that might otherwise strike Earth. Some objects are flung into distant orbits, while others are pulled into the planet itself. In 1994, astronomers witnessed the comet Shoemaker-Levy 9 breaking apart and crashing into Jupiter, leaving scars larger than Earth. While Jupiter does not protect us from everything, its presence reduces the number of potential catastrophic impacts. A giant guardian orbiting beyond Mars, shaping the flow of cosmic traffic. The solar system travels around the galaxy. Our Sun and planets are not stationary. They orbit the center of the Milky Way at about 828,000 kilometers per hour, completing one galactic orbit roughly every 225 to 250 million years. During this journey, the solar system moves through spiral arms, interstellar clouds, and changing cosmic environments. This galactic motion subtly influences comet orbits, cosmic ray exposure, and possibly even Earth's long-term climate cycles. Right now, we are on a slow voyage around the galaxy's core, carried along in a cosmic dance that began long before humans and will continue long after. The moons of Uranus orbit at odd angles. Because Uranus is tilted on its side, its moons also orbit in unusual planes, aligned with the planet's equator rather than the Sun. This means their orbits are tilted almost 98 degrees relative to the solar system's general plane. Some moons rise and set in strange directions, and their seasons are unlike anything on Earth. Uranus's unique orientation creates a moon system that behaves differently from all others. A tilted, sideways miniature world circling a tilted, sideways planet. The Sun accounts for nearly all the light in the solar system, except for faint starlight and occasional flashes from comets. Every ray of light that illuminates the planets and moons comes from the Sun. Its photons scatter off clouds, ice, rock, and dust, giving worlds their glow. Even the light of the moon is simply reflected sunlight. In the darkness of interplanetary space, the Sun's brilliance defines day and night for every orbiting body. Without it, the solar system would be invisible, drifting in eternal blackness. The Sun is not just the center of gravity, but the source of every shadow and shine. Saturn's moon Titan has a thick atmosphere. Titan is the only moon in the solar system with an atmosphere denser than Earth's. Its air is made mostly of nitrogen, with traces of methane and complex organic molecules. This thick atmosphere supports weather systems, clouds, and rain made of methane instead of water. It is so dense that a person could strap on wings and glide through it with ease. The surface beneath is carved by rivers and lakes of liquid hydrocarbons, making Titan a unique world where chemistry takes the role of water's cycle on Earth. Titan is a moon with skies, storms, and alien rain. The Sun generates space weather. The solar wind, magnetic storms, and flares from the Sun create what scientists call space weather. These events can disturb Earth's magnetosphere, disrupt satellites, and even affect power grids on the ground. Strong solar storms can generate brilliant auroras, but also pose risks to astronauts and technology. Predicting space weather is a growing field of science, helping to protect our modern infrastructure. Just as Earth has weather in its skies, space itself has weather shaped by the Sun's changing moods. Many comets come from the Oort cloud, while short-period comets originate in the Kuiper belt. Long-period comets likely come from the distant Oort cloud, a spherical shell of icy objects surrounding the solar system, disturbed by passing stars or galactic tides. These comets can be flung inward on orbits lasting thousands or even millions of years. When they near the Sun, they flare into brightness, producing spectacular tails. Each is a messenger from the farthest frontier, carrying ancient ESAs from the solar system's frozen edge. Earth's atmosphere makes it unique among terrestrial planets. Unlike Mercury, Venus, or Mars, Earth has a thick atmosphere rich in nitrogen and oxygen, shaped and maintained by life itself. Plants and microbes over billions of years have released oxygen, which now makes up about 21% of the air. This breathable atmosphere protects us from harmful radiation, stabilizes temperature, and sustains oceans. It is both a shield and a life support system, intricately linked to the biosphere. No other known rocky world has such a balance. making Earth a rare blue oasis in a sea of barren landscapes. Mars has the largest dust storms in the solar system. Dust storms on Mars can grow so large they cover the entire planet. These storms are fueled by fine dust, temperature differences, and atmospheric circulation. Once started, they can last for weeks or months, dimming sunlight and altering temperatures globally. The thin atmosphere allows the dust to stay suspended for long periods, creating a reddish haze across the sky. For robotic explorers, these storms can be dangerous, blocking sunlight from solar panels and reducing visibility. For Mars itself, they are a restless cycle of wind and dust that never fully settles. The Kuiper Belt holds dwarf planets and icy relics. Beyond Neptune, the Kuiper Belt stretches outward, filled with frozen objects left over from the solar system's birth. Among them are dwarf planets like Pluto, Haumea, and Makemake, along with countless smaller bodies. These objects are remnants of the protoplanetary disk that never merged into larger worlds. Some follow stable orbits, while others are disturbed by Neptune's gravity. The Kuiper Belt is a cold frontier, a frozen archive preserving the early history of planet formation. Waiting silently in the dim sunlight, far from the warmth of the inner solar system, Earth is the only known planet with life. Despite decades of searching, Earth remains the only world where life is confirmed. From microscopic bacteria to vast forests and oceans teeming with animals, life has transformed the planet. It has shaped the atmosphere, carved ecosystems, and left fossils in stone. While Mars, Europa, or Enceladus may hold the ingredients for biology, none have yet shown proof. For now, Earth is unique, a living planet among silent neighbors. It reminds us that life, though it may exist elsewhere, is precious and fragile where we know it. The solar system is mostly empty space. Despite the presence of planets, moons, asteroids, and comets, the vast majority of the solar system is a vacuum. Distances between planets are immense. If Earth were the size of a marble, the Moon would be a few centimeters away, but Mars would be several meters off, and Pluto would be more than a kilometer distant. Between these objects lies mostly emptiness, with occasional dust and particles carried by the solar wind. The solar system is a sparse realm, where islands of matter float in an ocean of space. Jupiter's moon Io is locked in a gravitational tug-of-war. Io's extreme volcanism is powered not only by Jupiter's gravity, but also by the pull of neighboring moons Europa and Ganymede. These constant tugs stretch and compress Io, generating intense tidal heating. The result is a surface reshaped by lava flows and eruptions. With volcanoes more active than any on Earth, Io's orbit is kept in a resonance by its siblings, creating a cycle of stress and fire. It is a moon trapped in a never-ending struggle between icy companions and a giant planet, glowing with molten scars. The Sun will expand into a red giant. In about 5 billion years, the Sun will run out of hydrogen in its core and begin fusing helium. As it changes, its outer layers will swell enormously, engulfing Mercury and Venus and perhaps Earth as well. Its surface will cool, glowing red, while its luminosity increases. Eventually, it will shed its outer layers as a planetary nebula, leaving behind a white dwarf core. The Sun's peaceful yellow glow is only temporary. Its long future holds expansion, fire, and fading light. Some moons are captured asteroids. Not all moons formed alongside their planets. Some, especially around Mars, Jupiter, and Neptune, were likely captured from asteroid-like bodies wandering too close. Their irregular shapes and unusual orbits suggest they were seized by gravity rather than born in place. Mars's moons, Phobos and Deimos, may be such captures, as well as many of Jupiter's small outer satellites. These captured worlds are cosmic hitchhikers, remnants of collisions and wanderers drawn into planetary families. Saturn's hexagon storm is a mystery. At its north pole, Saturn has a strange hexagon-shaped storm system, first observed by the Voyager spacecraft and later studied by Cassini. The six-sided jet stream rotates with the planet, maintaining its shape for decades. Scientists have reproduced similar patterns in fluid dynamics experiments, but the exact reason Saturn hosts such a perfect hexagon is still debated. It is a weather feature unlike any other in the solar system. A polygon of clouds spinning endlessly in the cold. Comets lose material each time they visit the sun. When comets approach the inner solar system, sunlight heats their icy surfaces, releasing gas and dust into tails. With each passage, they lose some of their mass. Eventually, many comets either break apart completely or become inert, leaving only rocky remnants. Some meteor showers on Earth, like the Perseids, come from dust left behind by such fading comets. They are beautiful but temporary travelers, gradually eroded by their journeys until nothing remains but memory and dust. Earth's core powers its magnetic field. Deep within Earth, the outer core is a swirling ocean of molten iron and nickel. As this liquid metal moves, it generates electric currents, which in turn create the magnetic field surrounding our planet. This field shields Earth from harmful cosmic rays and solar wind. Without it, the atmosphere could be stripped away and life endangered. The dynamo within Earth's core has kept the field alive for billions of years, though it occasionally shifts and reverses. Our planet's heart of metal is not just structural. It is a protective engine of magnetism. Neptune's moon Triton is geologically active. Despite being far from the Sun, Triton shows signs of cryovolcanism, with geysers that spew nitrogen, gas, and dust into space. Its surface is young and varied, marked by ridges, plains, and frozen lakes. Triton's retrograde orbit suggests it was captured from the Kuiper belt, and this capture may have fueled its internal heating. Today, it remains one of the most intriguing places in the outer solar system, a frozen moon with shifting, icy landscapes and a restless interior. The planets orbit the Sun counterclockwise. Viewed from above the Sun's north pole, almost all planets orbit in the same counterclockwise direction. This shared motion comes from the solar system's origin in a rotating disk of gas and dust. The rotation set a common direction for planets, moons, and smaller bodies. Exceptions exist in axial tilts or captured moons, but the general harmony remains. The planets spin around their star in a shared ancient rhythm, following the imprint of their birth cloud. The Oort cloud may hold trillions of objects. This vast, distant shell of icy bodies is thought to surround the solar system far beyond Pluto, though never directly observed. Its presence is inferred from the paths of long-period comets. Estimates suggest it may contain trillions of icy planetesimals, scattered remnants from the solar system's formation. Some were likely flung outward by Jupiter and Saturn's gravity billions of years ago. Today, they drift in the deep freeze of interstellar space, a silent halo of frozen debris marking the farthest edge of the Sun's reach. Earth's atmosphere glows at night. Even when the Sun has set, Earth's upper atmosphere emits a faint glow called airglow. Caused by chemical reactions high above the surface, this light can appear green, red, or yellow when viewed from space or with sensitive cameras. Airglow is different from auroras, which are driven by solar particles. Instead, it comes from the recombination of atoms and molecules that absorb sunlight during the day. Though faint to the naked eye, airglow wraps the planet in a delicate, constant shimmer, reminding us that Earth's atmosphere is always alive with subtle light. Some moons have subsurface oceans. Beneath their icy exteriors, moons like Europa, Enceladus, and Ganymede are believed to hide liquid water oceans. Heated by tidal forces or residual energy, these oceans may contain more water than all of Earth's oceans combined. Evidence comes from geysers, magnetic measurements, and surface features that suggest liquid beneath. These hidden seas are among the most promising places to search for life beyond Earth. Dark, alien oceans sealed under ice, warmed from below, waiting silently in the cold reaches of the outer solar system. The sun rotates at different speeds. Unlike a solid body, the sun is made of plasma, and its equator rotates faster than its poles. At the equator, it completes one rotation in about 25 days, while near the poles, it takes more than 30. This differential rotation twists magnetic fields, storing energy that can erupt as solar flares or coronal mass ejections. The sun's uneven spin is a key driver of its dynamic activity, fueling cycles of magnetism and storms across its blazing surface. Mercury has extreme temperature swings. As the closest planet to the sun, Mercury endures scorching daytime temperatures of over 400 degrees Celsius. Yet, with no thick atmosphere to retain heat, nights plunge to below -170 degrees. This wild swing of nearly 600 degrees makes Mercury one of the most extreme planets in the solar system. Some craters at the poles, however, remain in permanent shadow and are cold enough to preserve water ice, a stark contrast to the blazing heat just beyond their rims. Mercury is a world of fire and frost, both searing and frozen in the same orbit. Asteroids preserve the solar system's history. Most asteroids are unchanged since the early days of planet formation. Unlike Earth, which has weather and tectonics, these small bodies have remained mostly unaltered for billions of years. Studying them offers a direct glimpse into the solar system's past, revealing its composition and chemistry. Meteorites that fall to Earth provide samples, while missions like OSIRIS-REx and Hayabusa have collected pristine asteroid material. Each fragment is a time capsule from the solar system's birth, unchanged relics that whisper of origins written in stone. Saturn's moon, Enceladus, may host hydrothermal vents. Beneath its icy crust, Enceladus has a global ocean kept warm by tidal heating. Cassini detected plumes of water vapor containing salts, silica, and organic molecules erupting into space. These ingredients suggest that hydrothermal vents, like those on Earth's seafloor, may exist at the bottom of Enceladus's ocean. On Earth, such vents teem with life, independent of sunlight. If similar environments exist on Enceladus, they could provide a potential habitat for life. A tiny, icy moon, yet with the possibility of a living ocean world within. The planet's orbits shift over time. Planetary orbits are not fixed, but slowly change due to gravitational interactions. Over millions of years, eccentricities, tilts, and distances vary in cycles. On Earth, these cycles, called Milankovitch cycles, influence climate, contributing to ice ages and warming periods. Similar shifts occur across the solar system, gradually altering planetary alignments and resonances. Though subtle on human timescales, These orbital dances shape climates and histories over geological ages. The solar system is not static, but a slow, moving ballet of shifting paths. The Sun contains nearly 1 million Earths. With a diameter of about 1.4 million kilometers, the Sun could fit over 1.3 million Earths inside its volume. Its immense size and mass dominate the solar system, binding planets and comets with gravity. Yet, it is only a medium-sized star by galactic standards. Larger stars can swell to hundreds of times the Sun's size, while smaller red dwarfs are barely larger than Jupiter. The Sun sits in the middle, but to us, it is vast beyond comprehension. The glowing giant that makes life possible, Pluto has mountains of ice. On Pluto's surface, some mountains rise as high as the Rockies, but they are not made of rock. Instead, they are built of water ice, which is strong enough at Pluto's freezing temperatures to form towering peaks. These icy mountains sit beside plains of nitrogen ice that flow like glaciers, reshaping the landscape over time. The diversity of Pluto's surface surprised scientists during the New Horizons flyby, revealing a geologically active world at the edge of the solar system. Pluto is not just a frozen ball, but a complex, evolving planetesimal with peaks of frozen water. Venus has crushing atmospheric pressure. On its surface, the atmosphere of Venus is about 90 times thicker than Earth's, equivalent to being nearly a kilometer underwater on our planet. This immense pressure, combined with extreme heat of over 460 degrees Celsius, makes the surface environment incredibly hostile. Any spacecraft landing there is quickly destroyed, as happened to the Soviet Venera missions, which lasted only minutes to a couple of hours. The thick atmosphere not only traps heat, but also presses relentlessly on everything below. Venus is a planet under permanent atmospheric weight, a world of crushing skies. Jupiter emits radio waves. Beyond its visible storms and swirling clouds, Jupiter produces strong radio emissions. These signals are generated by its powerful magnetic field and the motion of charged particles within it. Some emissions come from interactions with its volcanic moon, Io, where electric currents flow along magnetic lines connecting the two worlds. These radio waves can be detected by instruments on Earth, allowing scientists to study Jupiter's magnetosphere from afar. The planet hums with invisible energy, a giant broadcasting silently across the void. The solar system formed from stardust. The elements that make up Earth, the planets, and even our bodies were forged in earlier generations of stars. Heavy elements like carbon, oxygen, and iron were created in supernova explosions and scattered into space. When the solar nebula collapsed, it gathered this material, mixing ancient stardust into new worlds. Every atom heavier than helium in our bodies once came from the heart of a star. The solar system is not just a collection of planets, but a recycling of cosmic matter, a continuation of stellar life cycles written in dust and fire. Mars has polar ice caps. At both poles of Mars lie vast ice caps made of water ice mixed with carbon dioxide frost. These caps grow and shrink with the seasons, as carbon dioxide freezes out of the thin atmosphere in winter and sublimates back into gas in summer. Beneath the seasonal changes, layers of water ice remain year-round, storing a record of climate shifts over millions of years. Like Earth's ice cores, Mars's polar regions may preserve a frozen history of its atmosphere, a record locked in ice waiting to be read. Some asteroids travel in pairs. Though many asteroids are solitary, a surprising number are binary systems, where two asteroids orbit each other as they circle the Sun. Some even have tiny moons. These pairs form through collisions, fission from rapid rotation, or gravitational captures. Binary asteroids reveal much about how these bodies evolve, how they spin, and how fragile rubble piles can hold together. Missions like DART, which tested asteroid deflection on the binary system Didymos and Dimorphos, show that studying pairs is not just science, but planetary defense. Double asteroids are reminders that even in small scales, gravity makes companions. The heliosphere moves through space. As the Sun orbits the galaxy, its solar wind carves out the heliosphere, a protective bubble around the planets. This bubble is not stationary. It drifts through interstellar space, changing shape as it encounters different regions of gas and dust. The boundary, the heliopause, shifts with solar cycles and galactic conditions. Like a moving shield, the heliosphere protects the solar system as it sails through the Milky Way, a vast bubble of magnetic breath blown by the Sun. The Moon's far side is different from its near side. While the near side of the Moon, always facing Earth, has large dark plains called Maria, the far side is much more heavily cratered and lacks similar wide basins. This asymmetry puzzled scientists for decades. One theory suggests that Earth's gravity influenced how the Moon cooled, causing thicker crust on the far side. Another possibility is that massive impacts shaped one hemisphere differently. When spacecraft first photographed the far side in the 1950s, it revealed a hidden, alien landscape unlike the familiar face we see in the sky. Solar flares can affect Earth. Powerful bursts of radiation from the Sun, known as solar flares, can disrupt communication systems, satellites, and power grids on Earth. These flares are often accompanied by coronal mass ejections, which send charged particles racing toward our planet. When they hit Earth's magnetic field, they can cause geomagnetic storms, producing brilliant auroras but also technological hazards. Space weather forecasting helps mitigate these risks, but the Sun's storms remain a potent reminder of our connection to its energy. The planets differ in rotation speeds. Some planets spin rapidly, while others turn slowly. Jupiter rotates once every 10 hours, making it the fastest spinner in the solar system. Venus, by contrast, takes 243 Earth days for a single rotation, slower than its year. These rotation speeds affect planetary shapes, weather, and atmospheres. Rapid spinners bulge at the equator, while slow ones develop extreme day-night contrasts. Each planet's spin is a reflection of its formation, history, and cosmic collisions, shaping its unique rhythm of day and night. Comets may have delivered water to Earth. One theory suggests that much of Earth's water arrived via comet impacts in the planet's early history. Comets contain frozen water and organic compounds, and collisions may have seeded the young Earth with these essentials. Isotopic studies of cometary water show similarities and differences to Earth's oceans, suggesting that both comets and asteroids contributed. The idea ties our oceans to the icy wanderers of the outer solar system, linking the blue seas we know to distant frozen travelers. Earth's magnetic field sometimes flips. Over geologic time, Earth's magnetic poles have reversed many times, with north becoming south and vice versa. These geomagnetic reversals happen irregularly, separated by hundreds of thousands of years. The process takes thousands of years and does not cause catastrophe, but it can weaken the field during transition. Rocks preserve evidence of past flips, locking in magnetic orientations as they cool. The next reversal may be tens of thousands of years away, or it could already be slowly starting. Earth's magnetism is not fixed, but part of a long, dynamic cycle. Neptune is the windiest planet. Winds on Neptune can reach supersonic speeds of over 2,000 kilometers per hour, faster than the speed of sound on Earth. These powerful currents sweep across the icy blue planet, driving storms and shifting clouds. The source of this extreme energy remains uncertain, but internal heat and atmospheric chemistry may play a role. Despite its distant, cold environment, Neptune is a planet of violent gales and restless weather. Asteroids can have moons. Some larger asteroids are accompanied by small companions, tiny moons that orbit them. These asteroid moons form when debris from collisions becomes gravitationally bound or when binary systems evolve. Observations and spacecraft flybys have revealed several examples, including Ida and its moon Dactyl, discovered by the Galileo spacecraft in 1993. Even among small bodies, gravity gathers satellites, echoing the patterns of planets and moons on a smaller scale. The Sun influences Earth's climate. Though human activity now drives modern climate change, the Sun still plays a role in long-term variations. Changes in solar output, sunspot cycles, and solar storms can alter Earth's upper atmosphere and affect weather patterns. Over millennia, cycles in Earth's orbit and the Sun's activity have contributed to ice ages and warm periods. The Sun is the ultimate source of Earth's energy. Its steady but variable heartbeat shaping climate across ages. Jupiter's great red spot is shrinking. This enormous storm, larger than Earth, has raged for centuries, but recent observations show it gradually decreasing in size. Once wide enough to swallow 3 Earths, it is now closer to 1.5. The cause of its shrinkage is not fully understood, but it may eventually fade away. Even so, the red spot remains a symbol of Jupiter's turbulent atmosphere, a swirling scar of time and weather. Earth is a water world. More than 70% of Earth's surface is covered by oceans. This abundance of liquid water sets it apart from every other known planet. Water drives the climate, sculpts landscapes, and sustains life. From deep trenches to icy poles, Earth's water cycle links sky, land, and sea in a continuous flow. Though other worlds may have hidden seas or icy shells, none match Earth's vast open oceans, blue and endless from space. Saturn's moon Enceladus reflects nearly all light. Enceladus is one of the brightest objects in the solar system, with a surface covered in fresh, clean ice that reflects almost 100% of the sunlight that strikes it. This high reflectivity, or albedo, makes it shine like a cosmic beacon. Beneath the ice lies a global ocean, and geysers from its surface continuously resupply the icy coating. Enceladus gleams in the darkness, a tiny frozen mirror orbiting Saturn. Meteorites bring clues from space. Rocks that fall to Earth from space provide direct samples of other worlds. Some come from asteroids, others from the Moon or Mars. These meteorites contain minerals, metals, and even organic compounds, offering a record of the solar system's formation. By studying them, scientists uncover clues about planetary chemistry, water delivery, and even the possibility of life beyond Earth. Each meteorite is a fragment of cosmic history, delivered free by the universe. The solar system is not the only one. For centuries, we knew only of our own planets. But today, astronomers have discovered thousands of exoplanets orbiting other stars, many in systems with very different architectures. Some stars host hot Jupiters close to their suns. Others have multiple Earth-sized worlds in tight orbits. Our solar system is just one of many, a single example in a galaxy filled with planetary families. The night sky is full of other suns, many with worlds of their own. The sun will one day fade away. After becoming a red giant and shrinking to a white dwarf, the sun will cool slowly for trillions of years. Eventually, it will become a cold, dark remnant called a black dwarf, no longer shining. Though this future lies far beyond human timescales, it marks the final destiny of our star. The solar system will be gone, but the atoms within us will continue, part of the endless cycle of stars.